All right, everybody, we're going to go ahead and get this show on the road. We're starting into Chapter 2 now, describing location in a distribution. And obviously, I'm using someone else's PowerPoint, so obviously give credit where credit's due. This is a PowerPoint that was located on a website, that StatsMonkey, which is a favorite website of mine, that I know several people use. So I'm going to go through this with my spin on it. This is, again, describing location in a distribution. All right, so what we start with here is some sample data, okay? And we got a bunch of data, and these are test scores for some small class. Jenny, our student, is noted in red. So she got an 86, and you can take a look at the rest of the data. The question is, how well did she perform on this test relative to everybody else in the class? All right, so what we can do is we can construct a stem and leaf plot. You can see that right there, right? You've got your 67, your 72. These are split stems, 73, 73, 74, right? So we do, we have a 6, 0 through 4, 6, 5 through 9, 7, 0 through 4, 7, 5 through 9, and so on, okay? And you can see it's fairly symmetric, okay? And she's definitely up in the upper part of the class. She's done pretty well. But we want to figure out how well did she do relative to her peers. Okay, well, here's her statistics. There are 25 students in the class. The average was an 80. Okay, the median was also an 80. It's a it's a very symmetric distribution, maybe not perfect. The standard deviation, you can see, is 6. Okay, we have the minimum, the maximum, the Q1, Q3, and so on. Okay, so she's above average for sure, and the question is, how above average is she? Okay, so what we're going to talk about here is something called a standardized value. This is also known as a z-score. And what a z-score does is tells you relative to the mean and the size of the standard deviation, how far away from the mean are you? Right. So the formula is down here. Z equals x, her score, minus the average score, divided by the standard deviation of the scores. Okay. So it gives you a relative measure based on how far away on average most scores are. That's the standard deviation. Based on that is kind of a measuring stick. Okay. How many of those measuring sticks is she away from the mean? Let's look at the calculation. All right, so we have this test data in Julia's score again, and according to Minitab, and Minitab is simply a software program. We could have said according to the TI calculator, that would have been fine, but it's a software program. According to Minitab, the mean test score was 80, and the standard deviation was 6.07. So Julia's score is above average. Okay, her standardized z-score is, and we just plug it in, x minus 80. 80 is the mean, 6.07 is the standard deviation. We plug hers in, and we find out that her score is 0.99. Her standardized z-score is 0.99. Okay, what that means is that she's almost one standard deviation above the mean. Okay, if we think of the standard deviation, and again, this is kind of a relative idea, if we think of the standard deviation as the average distance from the average, okay, that's just an intuitive kind of way of thinking about it, then she is almost exactly one of those measuring sticks, exactly one measure of average above the mean. Okay, so we can ask about Kevin as well. Okay, and where did Kevin go here? Kevin is a 72. Okay, you can see his is in blue now. Okay, but Julia got an 86. So 86 minus 80 over 6.07 is a z-score of 99. So she's above average. She's almost a full z-score above average. Okay, Kevin got a 72. Now he didn't do as well. But to get a sense of how far below average he is, he's negative 1.32 below average. It's a negative z-score. Okay, so he did not do as well. Okay, and he did worse in some sense than Julia had done better. So Julia is above average. She's not quite as above average as Kevin is below average, unfortunately for Kevin. Okay, Katie, who's got a score of 80, and there's the green right there for the 80, okay? She got the average score. What does that mean? Her z-score is 0. She's right at the middle. Okay. All right. Again, we can, there's a stem leaf plot. Okay. All right. Let's compare scores. So obviously, we can see kind of Katie's obviously above average, Kevin's obviously below average, Jenny's above average, Kevin's below average, and Katie is average. Okay, where this is not value judgments about them, we're talking about their test scores. So we can use standardized values to compare scores across two different distributions. And this is why standardized scores are really pretty cool. Okay, so On a stat test, the mean was an 80, the standard deviation was 6.07. Okay. Suppose, however, there's another class, you're taking chemistry, and the mean on a chemistry test is a 76 and a standard deviation of 4. So on average, people are scoring a little bit lower, but the spread of test scores is smaller, right? People aren't scoring quite as high or quite as low. Again, we don't know if it's symmetric at this point, but we do know that it's some people are above and some people are below. Okay, so Jenny got an 86 in stat and an 82 in chem. Now again, the average score in chem is less than the average score in stat, so in some sense that's not quite as bad. And the question is, did she do better in statistics relative to everybody else, or did she do better in chemistry relative to everybody else? And that's kind of the question we're going to ask here. She's above average in both classes, but because the variability in chemistry is so much less than statistics, it's hard to get a sense of how much better or worse she is in one class or the other. Okay, so which test did she perform better on? So here's her z-score for statistics, 0.99. That means relative to everybody else in the class, she did one z-score, just about one z-score better than the average. Okay, let's compare that to chem. Okay, in chem, her score is an 82. And now the mean was 76, the standard deviation was 4. So when we compute a z-score here, we get a z-score of 1.5. So relative to everybody else in the class, she actually did better on the chemistry test than on the stat test, even though her score is less on the chemistry test than the stat test. Okay, and this makes a lot of sense, frankly, right? There are some tests that are harder than others. Okay, what we're saying here is if this is the same group of kids, perhaps the chem test is harder, or perhaps the students are better at statistics. Okay, or have more experience in statistics. Okay, but now we have a way of comparing two different distributions to one another to get a sense of how does one person perform on one test versus another. Okay. So again, although she had a lower score, she performed relatively better in chemistry. So this is one way of comparing two distributions. I like z-scores a lot. It allows us to compare two incomparable things, right? We can get a sense of how much more exceptional is one person in one discipline versus another discipline, right? If you take a leading scorer in a great quarterback in football versus a point guard in basketball, how can you even begin to compare them? Well, maybe we could compare z-scores for the two because they're two different things, but we can compare all the great quarterbacks to all their peers, and we can compare all the great point guards to all their peers, and then figure out, well, how much better is Dwayne Wade than the rest of the team, than the rest of the point guards playing, versus how good is Tom Brady, right? So you get a sense there. Okay. All right. The other way we can compare two things within a distribution is this thing called percentiles. So we've actually dealt with them already. Okay. So what we're going to do here is we're going to look basically back at quartiles. Okay. Quartiles, percentiles. Ooh, right. Okay. So Jenny got an 86. And that was 22 of the 25 scores are less than or equal to 86. Okay, so Jenny is in the 22 divided by 25th. That's the 88th percentile. Okay, okay. It's another measure of relative standing, percentile rank. Where is she? Okay, so the pth percentile is defined as the value of p% of observations below it. Okay, so the median is the 50th percentile. The mean, the mean is the 50th. This is incorrect. The median is the 50th percentile. Okay. Pardon me. The mean is the 50th percentile if the graph is symmetric. This is a useless statement here. I would not even write that down. The median is the 50th percentile. The mean can be the 15th percentile, but it's not what it means, so I wouldn't even go there. Q1 is the 25th percentile. 25% of observations are below Q1, or at or below Q1, I should say. Right? Q3 is the 75th percentile. 75% of observations are at or below the Q3. The maximum, obviously, is the 100th percentile. All the observations are at or below that. Okay. Here's our stem and leaf plot again, and notice that we can actually count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 22, all the way to number 6. Okay, the number 6. That's with her score, right? And we can get a sense there are 3 above, right? So there are 3 above, there are 22 or at or below 6. Okay, so that's the the 88th percentile. Okay, so percentile rate gives you a sense of they're both measures of relative standing. A z-score tells you the how is the median, pardon me, how much better or worse is the score that you got relative to the mean? Okay, the percentile says, well, where are you in a rank, right? And they're both useful in different observations. Close to my own heart is my daughter, right? Every time we go into the doctor, they say, well, Billy is actually in the 75th percentile for height and weight right now. That's true. And what that means is that 75% of babies with her characteristics are her size or smaller. Okay, that's what a percentile means. Okay, that's the strict definition of a percentile.